Hello friends, so today we are going to solve the questions from the year 2010, 2011 and 2012. From the year 2012 rather, we have total of 6 questions. From 11 we have 2 questions and from 12 we have 3 questions. So total we are going to solve 11 questions. So in the first question, it was asked in the year 2010 and it states that a biconvex lens of focal length 15 cm is in front of a plane mirror. The distance between the lens and the mirror is 10 cm. A small object is kept at a distance of 30 cm from the lens. The final image is. In this case, it is a combination of a biconvex lens and a plane mirror. And we can just draw an approximate figure for that. And before that, we should keep one thing in mind, that the focal length of biconvex lens is given as 15 cm and the object is kept at a distance of 30 cm, which is exactly the double the focal length. Okay. So we can draw an approximate figure. Let us suppose this is the principal axis and we have a convex lens and there is a mirror somewhere here, and the distance between the mirror and the lens is given as 10 cm and the object is kept at a distance of 30 cm from the lens. So this is our object, and like I said, that the first thing we notice is that the object is placed at a distance of 2f from the lens. Object is placed at a distance of, that is our twice the focal length. So therefore we can say the first image will be formed at a distance of 2f on the other side. It means on the back of the, you can say to the right of the lens. So you can say first image let us suppose that we call as I1 will be formed at a distance of 2f on the other side. So therefore if we extend, so the image I1 will be here somewhere and this distance will be our, once again, 30. So we get that from the mirror the I1 will be at a distance of 20. And we know that in case of mirror, the object and the image are at a same equal distance from the mirror. Okay. So therefore, the second image that will be formed because of the mirror will be at a distance of 20 centimeter from the mirror. So we already have the distance between the lens and the mirror is 10. So we can say that at a distance of 10 centimeter, the second image will be formed. So this is our I2. So that the total distance from the mirror is our 20 centimeter. So we can say that on the other side, and this image I1 will behave as a virtual image, will be virtual image, for the mirror. So I1 will be the virtual image for the mirror. That's why we can say that the second image will be formed at a distance of 20 centimeter in front of the mirror. Okay. We can say that the second image, which is our I2, will be formed at a distance of 20 centimeter from the mirror, or we can say 10 centimeter from the lens. So totality, we found out that up till now we have two images, I1 and I2, and 10 centimeter from lens on the to the left hand side, to the left side of the lens, to left side of lens. So now we can use the formula to find out the final, and this I2 will be going to act as a object for the final image. You can say image I2 will act as a object for final image, and let us call that final image as I3. And in order to find out this I3, we can use the simple formula that our 1 upon V minus 1 upon U is equal to 1 upon F. And from here we can say that our U will be equal to our plus 10. So this gives us 1 upon V minus 1 upon plus 10. Focal length is our 1 upon plus 15. So this gives us that our V will be equal to 16 centimeters. So it means the final image will be at a distance of 16 centimeter from the mirror. Okay. One second. Yeah. So for the option is, it is a 16 centimeter from the mirror and the image will be real. So option number B is the correct one. So let me write it here, and thus the final image, that is I3, is at a distance, one second, there is some, I think, calculation mistake, let me check. So you can say my 1 upon V is equal to 1 upon 15 plus 1 upon 10. We get the LCM as 30, and this comes as 2 and this comes as 3. Yeah, now it's coming correct. And this is about 5 oblique 30 and giving us 1 upon 6. Okay. Sorry, I made a mistake. I found out the total. So we get 6 centimeter, because the formula which we used is with respect to the lens. So the image will be 6 centimeter from the lens. And so I3 will be somewhere here. And this distance will be our 6. But in the question, all the options are with respect to the mirror. So therefore, from the mirror, we can clearly see that this distance will be our 16. It says from the lens. Therefore, from mirror, it will be equal to 6 plus 10, coming as 16 centimeters, and this image will be real. Now the option B is correct. Option B is correct. We come next question, and here it is given that an image of an object approaching a convex mirror of radius curvature 20 meter along its optical axis is observed to move from 25 by 3 meter to 50 upon 7 meter in 30 seconds. What is the speed of the object in kilometer per hour? So we have to find out the speed of the object in kilometer per hour. So for that, let us write out what are the things given to us. The first thing given is to a radius of curvature. We have radius of curvature, that is a capital R, and that will be about 20 meters. Then we have the image initial distance, and we have the image final distance. We have image initial distance, which is, let us suppose, our D1, and that is our 25 by 3 meters, and we have image final distance, let us suppose that is our D2, and that is a 50 upon 7 meters. Okay, and the time interval is our 30 second. Time interval, that is t, is our 30 seconds. So based on the radius of curvature, we can easily find out the focal length. So first is that we can say focal length, that is of f, is equal to half of the radius of curvature, which is our 20 divided by 2, giving us 10 meters. Okay. Then one second, I think there is some problem in the data. Let me check. Okay, it's look good. And yes, so we can say that initial distance is, let us suppose d1, let us call that v1. This was confusing for me. So this is our v1 and this is our v2. That's correct. And we just found out the focal length. Then we are going to use the mirror formula for initial distance as well as the final distance. So we can say one upon f, 1 upon v1 plus 1 upon u1, and 1 upon f is our 1 upon 10, and v1 is our 25 upon 3 plus 1 upon u1, and this gives us that our u1 will be equal to minus of 50 meters. Similarly, we can do for the final distance also. 1 upon f, 1 upon v2 plus 1 upon u2. So rest of the values are same except our v2, that is 1 upon 50 upon 7 plus 1 upon u2. So this gives us that our u2 is equal to is 7, let me write it here, 1 upon u2 is equal to, become this as 1 upon 10 minus 7 upon 50. This looks good. And we get this as 50, and this is our 5 minus 7, and this is our 1 upon u2. And this gives us that our u2 is minus of 25. So now we know the distance between the initial and final object distances, and we also know the time. So we can say the distance traveled by object let us suppose that is our delta u. So delta u will be our u2 minus of u1, and this is equal to minus of 25 and minus of minus 50, which gives us 25 meters. Now we have to find out the speed. That is our speed will be our delta u upon time, and delta u is our 25, time is our 30 seconds, and this comes as 5.6 meter per second, but we are supposed to find out in kilometer per hour. So this comes as 5.6 multiplied by, this will be 18 upon 5 kilometer per hour, which gives us 5 goes with 5 and this goes by 3, and coming as 3 kilometer per hour. Okay. The speed was 3 kilometer per hour. That was supposed to find out. So next question. It was also asked in the year 2010, and it states that a short linear object of length b lies along the axis of concave mirror of focal length f at a distance u from the pole of the mirror. The size of the image is approximately equal to. And in this case, we are given that the object is a short linear object. And if the size of the subject is, you can say, short, and then we can say that the magnification is going to vary linearly with the distance from the pole. Okay. So that's why this term is mentioned here, short linear object. So you can write that for small objects along the axis, the magnification varies linearly with the distance from the pole. With the distance from pole. And here the object is lying, you can say, along the principal axis. Okay. So therefore the longitudinal magnification will be applicable. Object lies on the lies along the principal axis. Lies along the principal axis. So you can say that longitudinal magnification applies. Longitudinal magnification applies. And we can write that formula, that longitudinal magnification, that is of m, is approximately equal to v upon u and its whole square. And we also know that 1 upon f is equal to 1 upon v plus 1 upon u. So from here we can write our v will be equal to uf divided by u minus f. And we can easily substitute the value of v in the magnification equation. So we get our magnification m will be equal to, we get this as uf divided by u minus f whole divided by u, and this is our whole square. So u goes with u, and this comes as f upon u minus f and its whole square. Therefore we can say that if the size of the image if that is represented as b prime will be equal to m multiplied by b. M is a magnification we just found out, so this comes b multiplied by f u minus f and its whole square. So therefore option number D is the correct one. Option D is correct. Come to the next question. It was also asked in the year 2010, and it states that the focal length of a thin biconvex lens is 20 centimeter. When an object is moved from distance of 20 centimeter in front of it to 50 centimeter, the magnification of its image becomes from m to 5 to m to 50. Then the ratio of m25 to m50 is. So here we have two object distances, and based on this we can find out the image distances, and then we can use the magnification formula. So we are given the focal length of lens, that is of f, which is our 20 centimeter. Then we are given as initial object distance, let us call that as 1, and we say that u25 is equal to 25 centimeter, and then we have object distance 2, let us call that u50, and this is our 50 centimeter. So based on this, we can find out the image. So we can say image distance that is our V25 and V50 corresponding to U25 and U50. So we can use the lens equation, that is 1 upon f is equal to 1 upon V25 minus 1 upon U25. So this gives us 1 upon V25 is equal to 1 upon f plus 1 upon U25. Okay. And that will be 1 upon f is our 1 upon 20, and this is our plus and minus of 25. So this comes at V of 25 will be equal to 100 centimeters. Similarly, we solve it for 1 upon f is equal to 1 upon V upon 50 minus 1 upon U upon 50. So this gives us that V of 50 will be equal to 100 oblique 3 centimeter. So 3 centimeters. Now, based on this, we can find out the magnification. Okay, so let's find out the magnification of the first part. So we can say the M25 will be equal to, we have this as V25 divided by U25, and V25 is our 100 and U25 is our 25 minus, and this comes as minus of 4. Similarly, we can find out M50, which will be equal to V50 divided by U50. So we get this as 100 oblique 3 divided by U50 is our 50, and this comes as minus 2 upon 3. Okay, and is to do minus. Now we have to find out the ratio. So we get the ratio of M25 to M50 will be equal to 25 was our minus of 4. This is minus 2 upon 3. So this gives us that the ratio is equal to 6. The next question. Okay, it was also asked in the year 2010, and it states that a large glass slab mu is equal to 5 by 3 of thickness 8 centimeter is placed over a point source of light on a plane surface. It is seen that the light emerges out of the top surface of slab from a circular area of radius r centimeter. What is the value of r? So we can draw an approximate diagram for that. And suppose this is our glass slab, and we have a point source that is kept somewhere here, and it says that the light emerges top of surface in the form of a circular area. Okay, so we can just draw a circular area in which we are going to get the light. So this is the circular area through which we are able to get the light, and its radius is given as r. So we can just draw from here. It will be like this, and this is given as r. And from here we can also draw one important conclusion, that as the light is not coming, let us suppose this is our A and let B. So it means entire light is coming within the points A and B. So beyond point A and B there will be a total internal reflection, or just at point A the refractive angle will be 90 degree. Okay, and similarly it is true for the B side also. So ray of light will be traveling this direction, and the refractive angle, if it is a normal, so the refractive angle R will be equal to 90 degree, and we can call this as angle of incident I, and similarly this will be also of angle of incident I. And let us suppose this is having a refractive N2, refractiveness of N1, and the width is given as 8 centimeters. So we have to find out the value of R. So we are given the refractive index of glass slab, which is our N2. So refractive index of glass slab, this value is our N2, and it is given as 5/3. Okay. And thickness of glass is also given. Let us suppose we call this as T. Thickness of glass slab is our T, and the T is our 8 centimeter, and the outside is air, so this is our air. So we can use the Snell's law, and we are also going to use the angle of you can say critical angle, because the total internal reflection is going to take place. So you can say that critical angle, that is our C, will be equal to critical angle. If we represent it as C, then we can write that sine of C will be equal to 1 upon the refractive index, that is our N2. So from here we can say our C will be equal to sine inverse of 1 upon N2. And we already know value of N2, that is 5/3. So we get this as sine inverse of 3/5. So this is our critical angle. And from here we can say that, let me write it, sine of C will be equal to 3/5, and from here we can write that our cos of C, cos of critical angle, we can easily write it as 1 minus sine square of C, and this comes as 4/5. So we found out both the critical angle as well as the, you could say, its cosine function. Okay. And we can say that because of critical angle, if we can use the tangent of that critical angle, you can say the tangent of critical angle will be equal to our radius divided by thickness. Okay. And in this case, let me put it here, that this I will be our critical angle, and similarly here it will be also critical angle, that is of C. T is the thickness, so this is our T, and therefore we get tangent of the critical angle, which was initially we assumed at I, it comes as R upon T. And tangent of critical angle, we can write it as cos of C divided by sine of C, sine of C upon cos of C, my mistake. You can write it as sine of C upon cos of C, and this comes as our R upon T. Sine C, cos C we already know, and we also know T. So sine C was our 3 by 5, cos C was our 4 by 5, and R we need to find out. T is our 8. So here 5 and 5 goes away. So we get that our R by 8 will be equal to 3 by 4. So this gives us that R is equal to 3 by 4 times 8, and this goes by 2. So we get that our radius is equal to 6 centimeters, which we were supposed to find out. Yeah. We come to the next question. And in this question, it was asked that in the year 2010, and it states that a ray OP of monochromatic light is incident on the face AB of the prism ABCD near vertex B at an incident angle 60 degree, as in figure, if the refractive index of the material of prism is 3, actually it should be root of 3, which of the following is or are correct? So we are given a prism which is just like a irregular prism, okay, and we are given the respective each angle, and the incident ray is on the AB at a angle of 60 degree with the normal. Okay, so we can just draw the figure later on. Okay. So let me draw for the first case that, okay, so we have these 4 options. It states that it gets totally internally reflected at the face CD. Okay, so this is your face CD. So we have to find out whether it is get totally internally reflected or not. So therefore, let us draw for part this one. So this is our and we are given angle as 60. This angle is given as 135. This angle is 75, and this is our 90 degree. This is our A, sorry, not A, but B. A, B, C, and D. And initially the ray is incident at P, and it makes an angle of 60 degree. So this is normal, so incident ray, and this angle will be 60 degree. And we are given the refractive index of material at square root of 3. So it will try to bend toward the normal, something like this, and it is going to strike it here. And we can just draw a normal here and try to find out the condition whether it is going to be totally internally reflected or not. So we can use, let us suppose this is our R1. At point P, we can use the Snell's law and find out the R1. So you can say at point P, Snell's law, let us call this as mu1, this as our mu2. So we can say that mu1 sine of I is equal to mu2 sine of R1. Mu1 is air, so its value will be obviously equal to 1. And this gives us that 1 multiplied by sine of 60 is equal to mu2 is our square root of 3. And this comes as sine of R1. And 60 is sine 60 root 3 by 2. Root 3 and root 3 goes away. So we are left with our sine of R1 is equal to 1 by 2. This gives us that our R1 is equal to 30 degree. So we got that our R1 is our 30 degree. Okay. And we need to find out what will be the angle of incidence. Let us suppose this point is Q. And therefore for that we can just use the, you can say, the property of quadrilateral, and that gives us that we are going to get the angle. Okay, let me draw it here. So this is our B and this is our C. This is our P point, and the ray is approximately going somewhere here, and this. So we know this as a 60. This angle is our 135. Okay. And this entire angle will be equal to 60 plus 30, that will be 120. Sorry. So we get this will be our 120, and we can find out our this angle, because the sum of the quadrilateral angle is our 360. So therefore we can clearly understand that it has to be 45. So we got this angle is our 45, and here this is our normal, so we are going to have this is our Q. So this comes as so therefore we can say that the angle of incidence of the ray will be our, this angle will be coming as also as 45, because the entire angle has to be 90 degree. So we can say that the angle of incidence at phase CD is our 45 degree. Okay. And now let me draw at point Q, the ray of light will try to enter the rarer medium from the denser medium. Okay, or we can say it hits the interface of the denser and rarer medium, and it may refract and pass to the rarer medium, or there might be a total internal reflection. So these are the two possibilities at Q. So we can write that at Q, the light ray hits the interface and the interface is our CD, hits the interface CD, that is of the denser and rarer medium, so from here we can say that it may refract or reflect. So reflect will be a total internal reflection. Okay. So we have to find out the condition for the reflection, that is total internal reflection, whether it is satisfied or not. Okay. So you can say that for total internal reflection, the angle of incidence must be more than the critical angle. Angle of incidence must be greater than critical angle. And critical angle, we already know the formula, that our C is equal to sine inverse of 1 upon mu. Mu we already know, so we get the sine inverse of 1 upon square root of 3, and this comes close to 35 degree. Angle of incidence is about 45, therefore we can say that angle of incidence 45 is greater than our 35, therefore total internal reflection. Okay, and that was our option number A. So this option is correct one. Option A is correct. A is correct. Okay. So now we can just remodify for the figure, and now the figure will be use this one, whether it works or not. Let us see. And so this will be our and finally we can just draw this one, last one, which will be okay. More or less this looks good. So this is our A, this is our B, and then we have a C, and then we have D, and the respective angles are given. So this is our 90 degree. Here we have angle of 60. Here we have angle of 135, and this is our 75. And our ray of light is incident at point P. So this is our point P, and here we can just draw a normal. Which can just, hopefully it moves, doesn't look like. So we have this as incident light. Okay, let me draw freehand, it's taking lots of time. So it will try to bend in this way, and normal here, total internal reflected, and it will be striking somewhere here. Okay. More acute angle, like here. Okay. And this angle was our 60. This angle we found out is of 30. So we have this angle found out 45. So obviously this angle will be also 45. And here we have a normal. So this was a P and this was a Q. Let us call this as point as R. And here we can also find out the angle of incident at AD. So we have this angle will be over 45. It is traveling this direction. And angle of incident with respect to the anything else? Oh, 1 second. I draw it a wrong place. Sorry. It should be here. Let me draw it once again now. So this is our normal incident ray, and here normal, and it comes to this point, and once again let us call this was our point P, this was our Q, and let us call this as point as R. And we already know the various angles that are 90, this was 60, 135, this we found as 45 rather, so 60, and here we come as 30, and this will be also 45, and this angle is our 75. So we can find out that we are going to have this angle will be also 45, and with the entire angle is 90 degree, so we can say that we are going to get this angle as 35 rather. Okay. And the critical angle, one second, here is the correct one, or am I doing wrong? Okay, and it will be traveling somewhere in this direction, and it says that ray comes out through face AD. Okay, at AD we have to find out whether it will be a total internal reflection or not. Okay, so let me sort it out first. And the angle at R, so this is my A, B, C and D. You can say at face AD we have the angle of incidence is 35, angle of incidence is 35. Okay, I think let's look 35. My mistake, one second, this cannot be 45 because normal is not parallel to this one, my mistake. Okay, so let us find out what will be the angle of incident here. So this will be our, you can consider this as a triangle, and this entire will be 90 degree, so this angle will be a 45. Okay, and if this is 45, so we can say our angle will be equal to, this will be coming as 10 and this will be 120, so this angle will be 60. If this angle is 60, then we are going to get this angle as 30. Now it's the correct one. So we can say angle of incidence is 30 and the critical angle is our 35. Okay, so you can say that which is less than the critical angle, which is less than critical angle. Therefore, the ray will come out of AD. The ray will come out of AD. So option B is also correct. Option B is correct. Okay. And now we can find out the angle of refraction, that is this angle. Let us suppose this is our R2. So we can say Snell's law at R we can write this as incident angle is, let us suppose the I is 30 and here the refractive index is our, which we took it as mu2. So this is our mu2 and this is our mu1. Mu2 is our square root of 3. Okay. And mu1 is our 1. So we can say Snell's law at this. We get that mu2 sine of I is equal to mu1 sine of R2, and mu2 is square root of 3, so this gives us square root of 3 sine of 30 is equal to 1, and we have sine of R2. So this gives us that our R2 will be equal to 60 degree. Okay. So we are given that the first incident angle is at a 60 degree, and we have to find out what will be the angle between the emergent as well as the final emergent as well as initial. Okay. And for that we can just draw the figure rather. So initially the ray was incident at an angle of 60 degree at point P. Okay. So this was at 60 degree. Sorry. So let me draw a point P only. So this is a point P, and we have a light which is incident on here, making an angle of 60 degree. Okay. And if we extend that ray of light somewhere here, and finally the light ray that finally is coming out from our point R. Okay. So we can just say, let us suppose the point R is somewhere here. So this is R, and the light ray is coming from here, and it is making at an angle of 60 or 30, 60. And this is our point R, and if we extend then backward like this and draw a parallel line here, so we are going to get this angle will be equal to 60. Okay. And we are going to get this over 60, and this will be our 30. So accordingly this angle will be also our 30. Yeah. So therefore the incident ray and emergent ray will be at an angle of 90 degree. So this was our incident ray and this was emergent ray. So this is our I and this is our E. So therefore we can say that angle between incident and emergent ray is 90 degree. So therefore the option number C is the correct one. D is not correct because it is asking for 120. So option number A, B, C and are correct. You can see option C is correct. Okay. So we come to the next question, and here it was asked in the year 2011, and it states that a light traveling in glass medium is incident on the glass air interface at an angle of incidence of theta. The reflected ray and the transmit intensities both as a function of theta are plotted. The correct sketch is. So here it is given the light ray traveling glass medium is incident on the glass interface. Okay, so let us draw a This is a glass medium, a ray of light that is traveling and making an angle of incidence as theta, and the ray is partially reflected as well as partially transmitted. So it will be transmitted, so this is our transmission and this will be our reflected. Okay. And from here figure we can say that, okay, from the graph we can understand that the theta of the value starts at a 0 degree. Okay. So theta 0 means the light ray is entirely perpendicular. Okay. If light ray is entirely perpendicular, then the entire will be the transmission. There won't be any, you can say, reflection. And the other will be our critical angle, and for critical angle we can say the transmission is 0, but entire thing will be totally internally reflected, or after critical angle the entire thing will be totally internally reflected, the transmission will be equal to 0. You can say that after critical angle, reflection that is of R, this will be 100%, and transmission that is our T will be equal to 0. Okay. So from the figure we try to understand which of these 4 matches the option. Okay. So from here we can see that at the critical angle, option number B as well as option number C are the close resemblance, where option number A as well as option number D fails this criteria of the critical angle. Okay. And we can also say that in option number B it states that there will be a 100% transmission at 0 degree. So let us analyze the option number B, which states that at 0 we are going to have a 100% transmission. Okay. And 100% transmission ideally is not feasible. There will be some portion which has to be reflected. We can just draw a straightforward conclusion, and you can say that even at 0 degree there is partial transmission and partial reflection. Okay. And reflection can be close to 0 but not equal to 0. Okay. So based on this we can say that option number C is the correct one. Option C is correct. We come to the next question. It was also asked in the year 2011. and it states that the water with the refractive index 4 by 3 in a tank, water in a tank is 18 centimeter deep. Oil of refractive index 7 by 4 lies on the water, making a convex surface of radius of curvature r 6 centimeter as shown. Consider oil to act as a thin lens. An object S is placed 24 centimeter above the water surface. The location of the image at x centimeter above the bottom of the tank, then x is. So we have to find out the position of the x, and the x denotes the location of its image above the bottom of the tank. So in this case, we are given that there is a we have a water. So this is our water, and then this is our oil, and then we have our air. So ideally we are having a three surfaces, and these three surfaces are, you can say that the object is placed at 24 centimeter, that is our S. Okay, S is given, and we need to find out what will be the position of the image. So in this case, we have to remember that the light coming from the object has to undergo refraction due to three mediums interacting with each other. Okay, so mediums are our air, oil, and water. So these are the three mediums. Okay, and the first medium will be between the air and the oil. Oil is acting as spherical, and so we can use the spherical lens formula in order to find out the image, which will be our intermediate image. So we can say that the light coming from the object has to undergo refraction due to three mediums interacting with each other. Okay, so let us consider case first. And case first is the refraction due to air and the oil, and oil is our surface, spherical surface. So we can say that refraction due to air and oil, and our oil is a spherical surface. Oil, which is our spherical surface. So therefore we can use the formula that mu2 upon v minus mu1 upon u is equal to mu2 minus mu1 upon r. We are already given the values. So we substitute, we get this as 7 upon 4 times V minus 1 upon minus of 24 is equal to 7 upon 4. U1 is our air, so this is minus 1 and divided by 6, radius of curvature, and this gives us that the V will be equal to 21 centimeters. And this will be the intermediate image that will be formed 21 centimeter away from the lens. Okay, lens basically is oil. So we can say this is intermediate image. Let us call that as I1 at 21 centimeter away from the lens. Away from lens. Lens is nothing but our oil drop. Now we come to the case 2. And case 2 is the other side of the lens, which is oil drop and water. Other side of lens, which is basically our oil drop and water. Okay. Once again, we are going to use same formula, that is our mu2 upon V minus mu1 upon U is equal to mu2 minus mu1 upon R. And the radius of other side, which is oil drop, is our radius of curvature rather, will be infinity because it will be almost flat and it is also given as thin lens. Okay, so therefore we substitute the values, we get this as 4 by 3 times V minus, and this will be 7 upon 4 upon multiplied by 21 is equal to 4 by 3 minus 7 by 4, and this is our infinity. So this gives us that our V is equal to 16 centimeters. Okay, here I forgot to mention that this I1, this will be acting as object, acts as object for the lens and water combination, for lens plus water. And therefore this will be our final image. Final image at 16 centimeter below the lens. Below the lens. And we need to find out the distance x, okay, from the bottom level of the x. Okay. So we get that from the bottom level of water, which is our x, so we can say our x is equal to 18 minus 16, giving us 2 centimeters. So we come to the next question, and in this case asked in the year 2012, and it states that a biconvex lens is formed with 2 thin plano-convex lenses as shown in the figure. Refractive index N of first lens is 1.5 and that of second lens is 1.2. Both curved surfaces are of same radius of curvature r, that is 14 centimeter, for this biconvex lens for an object distance of 40 centimeter, the image will be. So here it is basically a combination of two plano-convex lenses, and we can just draw the figure slightly in different way, showing these two lenses in a separate. So this is the first one and this is the second one, and radius of curvature for both is given as 14. This will be also 14 and here also will equal 14. The refractive index is given as 1.2 and here it is given as 1.5. So for 1.5, let us call this as our n1, and for 1.2 let us call it as n2. And the object distance, that is our u, is our minus of 40 centimeters. So it is, let us call this as, this part as first one and this is our second one. So you can say focal length of first, or we can say for first lens, our R1 will be equal to 14 and its R2 will be equal to infinity. So we can use the formula that 1 upon f1 is equal to, we have n1 minus 1 and 1 upon r1 minus 1 upon r2. So we substitute the values, 1.5 minus 1 and 1 upon 14 minus 1 upon infinity. So this gives us that our f1 is equal to 28 centimeters. Similarly, we can do for the second lens. For second lens, and in this we are going to have our r1 as infinity and r2 will be equal to 14. The same formula, so we can say 1 upon f2 is equal to our mu2 minus 1 and 1 upon r1 minus 1 upon r2. So we substitute the values and we get this as 1.2 minus 1, 1 upon infinity minus 1 upon 14. So this gives us that our f2 will be equal to 70 centimeters. So we found out f1 and f2. Now we can find out their combined focal length. So you can say that combined focal length given as f. So we can write up f is equal to 1 upon f1 plus 1 upon f2. So this gives us 1 upon 28 plus 1 upon 70. So our f will be equal to 20 centimeters. And finally, we are going to find the image for this entire combination. So we can use the formula, thin lens formula, that is our 1 upon f is equal to 1 upon v minus 1 upon u. So we get this as 1 upon 20, 1 upon v, and this is minus of minus 40. So this gives us that our v is equal to 40 centimeters. So this is the image distance, and option number B is the correct one. option B is correct. Next question. It was also asked in the year 2012, and it states that the Young double slit experiment is carried out by using green, red, blue light, one color one at one time. The fringe width recorded are beta G, beta R, and beta B respectively. Then we have to find out how they are going to vary. This is quite straightforward, and based on the formula for the fringe width, that is our beta is equal to lambda capital D divided by small d. So from here, beta is directly proportional to lambda. Okay. And we already know that the wavelength of our red is greater than the wavelength for the green and wavelength for the blue. So therefore, we are going to get that the beta for red is greater than beta for green is greater than beta for blue. So the option number RGB, that is D, is the correct one. Option D is correct. We come to the next question. Okay, this was passage based question, and here it states that most materials have refractive index n greater than 1. So when the light ray from the air enters a naturally occurring material, then by Snell's law, sine of theta 1 upon sine of theta 2 is n2 by n1. It is understood that the refracted ray bends toward the normal, but it never emerges on the same side of the normal as the incident ray. According to electromagnetism, the refractive index of the medium is given by the relation n is equal to c upon v, and where that is equal to plus minus of square root of mu r and epsilon r, where c is the speed of light, speed of electromagnetic waves in vacuum, v is the speed in the medium, and er and u are the relative permeability, permittivity and permeability of the medium respectively. In normal materials, both Er and mu r is positive, implying positive n for the medium. When both Er and mu are negative, one must choose the negative root of n. Such negative refractive index material can now be artificially prepared and are called as metamaterials. They exhibit significantly different optical behavior without violating any physical laws. Since n is negative, it results in a change in the direction of propagation of the refracted light. However, similar to normal materials, the frequency of light remains unchanged upon refraction even in the metamaterial. So based on this, we have two questions. So this is the first question, and we have the second question. Although the question, everything was lengthy, but the solution is, you can say, quite short and quite direct. So let us go for part 1, and we are given that the refractive index for material is plus minus square root of mu r and epsilon r, and we are also given, or rather we know, that the speed of light in medium, that is our v, is equal to c upon n, and n has, we write in the modulus because it can be negative for metamaterial, but speed is always positive. Okay, hence the modulus. So this is the important point here, that n can be negative for metamaterials, but you can say speed is always positive. Speed is always positive. Therefore, let us check the options that are available to us, and the option number B is the correct one, because in option number A it states that V is equal to C multiplied by the modulus of n, and this is dimensionally also incorrect. And if n is greater than 1, then speed is faster than the light, which is physically impossible. Okay, for specifically for this part, okay, we can say that this is dimensionally incorrect, or we can say dimensionally wrong rather. And also, if value of n is greater than 1, then our V will be that is speed is greater than the speed of light in vacuum. So this is also incorrect. So this option is cannot be true. Okay. And for speed of light, it says that V is equal to C, and this relation is only true if value of n is equal to 1. Okay. And so it is not, we can say, true only for the vacuum, not for the metamaterial. So this option is also incorrect. And option D, it states that the wavelength of light in the metamaterial is lambda m is given. We can just discuss that in detail. So we are given the option D as option D is given to us lambda m is equal to lambda air multiplied by n. Okay. And this is, we know that this is incorrect because we know that the lambda is our C upon frequency. Okay. And we know that the V is equal to C upon modulus of n. So based on this, we can write that our lambda of m will be equal to V upon F, which will be equal to C upon modulus n multiplied by F, and that gives us lambda of air and divided by modulus of n. So the correct relation should be actually lambda m is equal to lambda of air and divided by modulus of n. So this option is incorrect. So D is also incorrect. So only option correct is option number B. You can say option B is correct. And now we come to the graphical option. It states that for the light incident from air on a metamaterial, the appropriate ray diagram is. So for the ray diagram, we best know A can be easily explained with the help of the Snell's law. Keep in mind that this is with respect to metamaterial, all the 4 options. And for Snell's law, you can write that for part second, we can write that wherever Snell's law gives sine of theta 1 divided by sine of theta 2 is equal to our n2 upon n1, and the refractive index n that is given, n is equal to our C upon V is equal to plus minus square root of mu r and epsilon r. And for metamaterials, it is mentioned that the value of n is our negative. So we are going to use the Snell's law, and here we have already written sine of theta 1 upon sine of theta 2 is equal to n2 upon n1, and here our n1 is our air, refractive index approximately equal to 1, and n2 is our metamaterial, and it is given as a negative. Okay. So therefore we can write that our sine of theta 1 upon sine of theta 2 will be equal to n2. But it is mentioned that our n2 is negative. So here we given that our n2 is negative. Okay. And sine of theta 1 is positive, n2 is negative. Okay. So there are only two options, that I have my sine of theta 1 is my positive, so this gives us that sine of theta 2 has to be negative, okay, in order to get n2 as negative. Okay. So therefore if sine of theta 2 is negative, then we can say that our theta 2, this should be lying either in our third or it should be lying in fourth quadrant. Okay. But the refracted ray must emerge on the same side of the normal as the incident ray. Okay. We also know that a refracted ray must emerge on the same side of normal as the incident ray. And theta 2 is in third quadrant. Theta 2 is in third quadrant. Or we can say that the refracted ray bends away from the normal and emerges on the same side of the normal as the incident ray, same side of the normal as the incident ray. So therefore the option number C is the correct one. Option C is correct. Yeah. So I think this was the last one. Yeah. So these were the questions which were asked in the year 2010, 2011 and 2012. total of 11 questions. So this complete all the 11 questions. Thank you.